Hi, and welcome to 4.5 Mass and Weight. In this activity, we discover the difference between mass and weight. Basically, weight is just the force due to gravity. So the units for weight, since it's a force, are going to be newtons, and mass is mass. So the units are in kilograms. And then we'll talk about the acceleration due to gravity and the gravitational field strength and all that good stuff. All right. Number one, what is the magnitude of the force due to gravity? So they're looking for F sub g, the weight. What is the force due to gravity exerted on a 2.3 kilogram ball that is freely falling towards Earth? Now, since they tell you it's freely falling towards Earth, we can assume that g is equal to negative 9.8. Now, you could say meters per second squared if you want to say the acceleration due to gravity. You could even say newtons per kilogram if you're describing the gravitational field strength. The magnitudes of both are the same. It's basically the same thing. I think most of you guys are used to meters per second squared, so for number one, we'll leave it like that. And then the equation you're going to use is just a variation of Newton's second law. The acceleration, in this case the acceleration due to gravity, is equal to the net force divided by the mass. But since we're doing weight and mass and gravity, you could think of it as G is equal to Fg over m. And what we were doing in the previous activities, we were using that other formula, F equals ma. All right, well, instead of F equals ma, we'll just use Fg is equal to mg. And this is basically the same formula we're going to use over and over again in this homework assignment. So let's get right to it. Fg is equal to 2.3 times 9.8. Really, it's negative 9.8 because you're accelerating downward. The gravitational field strength is directed downward. And the force due to gravity, the force is directed downward. So 2.3 times 9.8, that's going to give you 22.5 newtons downward, negative 22.5 newtons. But technically they only asked for the magnitude, right? So we didn't have to specifically say negative. We're just showing the direction with the negative sign. They're only asking for the magnitude, so that would be the amount, 22.5 newtons. All right, number two. What is the mass of a person who weighs 152 newtons on Earth? Well, they're telling you 152 newtons. That's their weight. So you could think of it as W. Some people write the capital W for weight. I like to use Fg, the force due to gravity. That's the definition of weight, is the force due to gravity. They're asking for the mass. And again, we're on Earth, so G is equal to negative 9.8. We could even use newtons per kilogram. That's the gravitational field strength. 9.8 newtons for every kilogram at this position in the gravitational field. So again, Fg is equal to mg, 152 newtons. Technically, this should be a negative number since the force is acting downward, and we're looking for the mass times negative 9.8. So you divide, you get a negative divided by a negative, and that gives you a positive mass, which is a good thing because mass is scalar, there's no direction. And 152 divided by 9.8, that's 15.5 kilograms. That's not a lot of mass. It says a person's typically like 70 kilograms is the typical mass of a student that textbooks give. So 15.5 kilograms, that's like a toddler, if anything. All right, but that's the answer. All right, so let's see. It says, how much does a 45 kilogram stack of books weigh on Earth? The mass is 45 kilograms. We're on Earth, so it's negative 9.8. Let's switch back and forth. Meters per second squared. All right, so remember, you could think of it as acceleration due to gravity. You could think of it as the gravitational field strength. It's the same magnitude. It's just different units, and it's a different name for the same thing for our purposes. They're looking for the weight, so they're looking for the force due to gravity. Fg is equal to mg. Fg is equal to 45 times negative 9.8. And Fg is equal to negative 441 newtons. Moving right along. It says an astronaut weighs 900 newtons on Earth. He goes to the moon and weighs himself again with the same scale. He now weighs 150 newtons. What is the astronaut's mass? And then what is the gravitational field strength on the moon? And C is kind of like a tricky one. Let's see. Oh. All right. So an astronaut weighs 900 newtons on Earth. Fg is equal to 900 newtons acting downward. Technically, it's negative. And that's enough information to find the mass. We don't have to worry about what he weighs on the moon, because we know that G is equal to negative 9.8. We could think newtons per kilogram, meters per second squared. So we're looking for the mass. So Fg is equal to mg. Fg is equal to, we know what Fg is. It's negative 900 newtons. We're looking for the mass, negative 9.8. So negative 900 divided by negative 9.8 gives you 91.8 kilograms. So that's the mass of the astronaut. They go to the moon. Their weight changes. He now weighs less. He's in a smaller gravitational field, a weaker gravitational field. But his mass is the same. So he weighs less. So let's see. Based on this information, what is the gravitational field strength on the moon? In this case, it's not negative 9.8 newtons per kilogram. It's something different. It's less. So, but the thing that stays the same is his mass. He didn't like lose an arm or anything. It's not some crazy weight loss program. He has the same amount of atoms making up his body. So he has the same amount of mass. And now we're looking, well, actually, we're not looking for this. They tell you his weight on the moon is 150 newtons. That's the force pulling him downward. So we could do Fg equals mg again. See, it's just a lot of this formula. Negative 150 is equal to 91.8 kilograms times g, the gravitational field strength on the moon, which is negative 1.6 newtons per kilogram. It's about 1/6 that of Earth. All right, now C, kind of tricky. It says, is it correct to say that the astronaut loses weight when they go to the moon? Why or why not? Typically, well, we'll give the physics definition first. Yes, we could tell right away he loses weight. First, he weighs 900 newtons, then he weighs 150 newtons. So definitely, yes, from our perspective, he loses Fg. He loses a force due to gravity. The magnitude of the force due to gravity decreases. This, normally when people say, oh, I lost weight, they're saying they lost mass. It's kind of like a little trick of the words there. But technically they're asking for the weight, right? But does he lose mass? No, he does not lose mass. Okay. Number 5 says, a book with a mass of 0.7 kilograms is at rest on a table. What is the weight of the book? Very repetitive, this homework. Hopefully you guys get it by now. You shouldn't even be watching this video anymore. You should just be rocking through these on your own. What is the weight of the book? See if you can do it on your own. G is equal to, well, we could assume we're on Earth, negative 9.8 meters per second squared. So Fg is equal to mg. Fg is equal to 0.7 times negative 9.8. Fg is equal to negative 6.86 or negative 6.9 newtons. Okay, number 6 says, is the net force on the book in the previous question balanced, in equilibrium, or unbalanced? Explain your answer. In a sentence or two, explain your answer in a sentence or two, then draw a diagram of the forces acting on the book. It's a very weirdly worded question. I'm going to have to rewrite this for next year. They want a sentence or two and a free body diagram. So let's draw the free dot. Here's the book. What direction is the weight acting? The force due to gravity is acting downward. Fg. Well, now if that's the only force acting on this book, it looks like the net force would be down And the book should be accelerating downward through the table, but it's at rest. It's at rest on the table. So what's happening here? How could it be at rest if there's only this one force acting on it? Shouldn't it go downward? Well, there's another force that we're going to learn in the next lesson or two. The table actually pushes back up on the book with another force. This force is called the normal, or just F capital N, F sub N. This is the normal force. It balances out the weight. So if it's asking, is it balanced? Yes, it is in equilibrium. Balanced. Because, and I'm not going to write it out, but it's balanced because the normal force is acting in the opposite direction as the weight, and they're equal to each other in opposite directions, so the net force is 0. You could say that. The net force is equal to 0 newtons, not accelerating, at rest, constant velocity of 0 meters per second. Number 7. After decades of space exploration, an astronaut lands safely on Planet X. The first thing she wants to do is to experimentally verify the acceleration due to gravity on this strange new planet. Her experiment: the astronaut uses a vertical force of 175 newtons to lift an 87.5 kilogram boulder at constant velocity to a height of 0.35 meters above the planet's surface. What is the magnitude of the acceleration due to gravity on the surface of the planet? It sounds like a pretty complicated problem, but we are looking at a key term here. It's moving, they're lifting the boulder at constant velocity. If it's moving at constant velocity, that means the net force is equal to 0 newtons. She's using a vertical force of 175 newtons to lift the boulder. So let's draw a free body diagram. Here's the boulder. She is exerting a force. I'm going to call that FA for applied force. And it's 175 newtons upward. Well, if the boulder is moving at constant velocity, that means the net force is 0. It's not accelerating. So since it's not accelerating and the net force is 0, if there's an upward force of 175 newtons, what must the weight of that boulder be? That's right, 175 newtons, acting downward. The forces balance each other out. The boulder is in equilibrium, moving up at this constant velocity. The net force is 0 newtons, so that's how we know that the forces are balanced and they're equal to each other. That was kind of tricky. That whole conceptual thing gets you to the idea that Fg is equal to 175 newtons. So now we're looking for the acceleration due to gravity, the gravitational field strength. That's what we're looking for. And they also tell you the mass of the boulder. How nice of them. 87.5 kilograms. I'm saying them. I wrote this. All right. So G is equal to what? Well, we could use Fg or equals mg. Since we're looking for the gravitational field strength or the acceleration due to gravity, we could use this form of the formula. G is equal to Fg over m. Or you could use Fg equals mg. It's the same thing. All right, and we're looking for G. So we could plug in negative 175 newtons because remember the force due to gravity is acting downward and the mass is 87.5 kilograms. So what's the new acceleration due to gravity on planet X? It's negative 2 meters per second squared. To put that in perspective, like we said in the previous page, on the moon, the acceleration due to gravity is 1.6 meters per second squared. So this planet X, pretty small planet. It's only a little bit bigger than our moon. All right, that was 4.5, mass and weight. Hope you enjoyed it. Have a nice day.